All right, welcome to module number 26. We're now beginning the machine learning material, and we're going to start the machine learning material with two classification examples, which are taken from the textbook. Recall that in classification, a typical problem would involve here, we have a binary classification problem, and there's code online, both MATLAB and Python. Typically, you have data in some perhaps higher dimensional space. In this case, it's 2D space. And you're looking at the data, and you have training data and test data. And in the training data, the data is labeled. It could be blue and red and green, black and white, 0, 1, and 2, whatever. Binary, but it could be ternary or etc. And in the training data, you get to see for each of these places, as we're illustrating in the 2D plane, whether they're red or blue. And note that the red ones are circles, the blue ones are asterisks. And when there are going to be test data, you're trying to be able to predict whether they'll be red or blue. So the goal is to predict the class, to classify. Is the goal realistic? Well, that depends. Obviously, if the classes are well separated, it's easier. If there's more noise, it's harder. We'll talk about these things. But the structure of the classes is part of the issue here. Here, what we're seeing is that there are areas that, and I was moving my cursor, but just to highlight, there are areas where the blue and the red overlap. Then there are other areas where there's only red and other areas where there's only blue. And maybe next time I could do it, I could make this illustration with blue versus red colors. But you get the point that there are red regions, there are blue regions, but there are also mixed regions. And this leads to two conflicting goals that we want our classifier to achieve. On the one hand, we want a stable classifier. We don't want the classification. Is the test point red or blue? We don't want it to jump around a lot. So for example, in this shaded area, the area that I'm now shading that has both red and blue, there might be, suppose that you know the truth, the actual function that generates the classes. And if the truth is maybe some very complicated function, that would explain why in this shaded area, there are a lot of transitions from red to blue. But we don't, well, if we know the truth, then if the truth jumps around a lot, that's how it is. But in the real world, we don't want the truth, and we would prefer our classifier not to jump around a bit. Another issue is that we want our classifier to be accurate. And in the literature, this is referred to as low bias. So for example, maybe in the shaded area, you'll say, you know what, the whole thing, I'm going to call it red. Well, if it's red, there are quite a few blues there, and it's going to be a less accurate method. So a natural conflicting goal in classifiers, and recall, we're talking about trade-offs a great deal during the course, is that a stable classifier implicitly relies on the assumption of a simple function, kind of like Occam's razor, but it may have larger bias. It may be less accurate. So let's move on. So here's one approach how to classify. It's called the nearest neighbors approach. For each test point, recall, you have the training data, but now you're evaluating test data. For each test point, find the k nearest neighbors among the training samples. K nearest neighbors, that's why this classifier is often called k nearest neighbors approach. In the training data, among these k, there's going to be red and blue. And they're known, they're in the training data. And we're going to do a majority vote. For example, suppose that k was 11, and you had 7 reds and 4 blues. 7 is larger than 4, red. Now, this requires that you'll have, indeed, an odd number, and there are different tweaks to this. For example, you could say, look, I'm only going to make a decision if I have a solid majority of red and blue in that area. And if I don't have a solid majority, I'll pass. I'll say, look, I don't really know. So there, as you can imagine, there are twists and turns, features, how, and not features in the machine learning way, but tricks, how to make this a bit more interesting. But the bottom line, let's just keep it simple, majority vote. And now we said we're going to find the k nearest neighbors. How big should k be? So you could use a large K, you could use a small k, and let's evaluate that. So let's begin with, again, how big is k going to be? We're going to look at the k nearest neighbors. Let's take k equals 50. Now, note that I had 200 training samples. The number of red asterisks and, or rather red circles and blue asterisks in my 2D space was 200. And taking k equals 50, a quarter of the points is somewhat large. And on the one hand, this means that each test sample is being classified using a lot of neighbors, so it's very stable. And what you can see here, in small dots, I have small dots that are either red or blue. And you can see that here I'm trying to divide between above is blue, and I'll just write B, blue dots. And in the middle, we have red. And below, again, we have blue. So there are 3 regions. And note that I didn't sketch this so well, but the edges seem to be curvy, nonlinear. And there are reasons for that. Some of you who may want to read more about classifiers will be able to easily understand why. But bottom line, it's stable. On the other hand, we said that there's a trade-off between how accurate the method is and how stable it is. Yeah, it's not very accurate. It's noisy. And just as an example, and now let me kind of switch colors. In this area, as expected, it's making some errors. In this area, we seem to have blues, but they're in the red region for whatever reason. So we had an intuition 50 is too much because we have 200 training samples in total. Indeed, because 50 is large, it's stable, but it's noisy. So let's try a smaller number. What about 5? Now 5 might be on the small side. So what we're seeing here, again, let me try to sketch the regions. We have a blue region that starts here, and it seems to contain this thing, and this area is blue. And then we have, similar to before, in the bottom portion, we have a blue region. And in the middle, similar to before, we have a red region. However, in the interesting shaded region, the borders between the blue and the red are kind of jagged. So it's less stable because K is smaller. We're making a decision, we're making a majority vote based on a small group, but it seems to classify more precisely. If you'll go into that shaded region, there's some improvement. So maybe we should use minimal K, like K equals 1. Well, probably not, because then it'll be very unstable. So let's see that. So now we're sort of sampling the one nearest neighbor, a singleton neighbor, and this classifies the training data well. So in other words, things are accurate, but very unstable. So maybe it's prone to noise. So for example, if you look at the area that we discussed earlier, the reds and the blue are changing all over. But look here, that this region seems to be red, and let's see, and here there's some red here. Now, could that be noise? Now here we have a red and a blue in the training data that are very close. So could this be but just noise? Maybe. So to summarize, what we're seeing so far, we started with k equals 50, very stable, very inaccurate. We went down to k equals 5, looks pretty good. Going down to k equals 1, might be prone to noise. So we probably want a moderate k, a reasonable trade-off between stability and bias. And moderate k in this case might be 10 or 5. So let's continue. Can we choose k automatically? So what would it mean to have an optimal value of k? Of course, the more important it is for you for things to be stable. If you really want stability, you'll prefer a larger k. If you really want accuracy, you'll prefer a smaller k. So the trade-off here is really something that you can choose. But now let's think about it in a qualitative way. On the one hand, if there's more randomness, if the data is noisy, then probably we want to use a larger k to be confident about our majority vote. Now, what if we have a high dimensional space? Here we had 2 dimensions, and in 2 dimensions, neighborliness is sort of well defined. But in high dimensions, the whole issue of neighborliness is sort of obscure. And this is known as the curse of dimensionality, and you may want to read about it. I made some notes in one of the supplements. Now, okay, so large noise, increase k. High dimensionality, well, that might be the equivalent of randomness. What about large n? So for large n, on the one hand, we have a ton of data. We should probably be able to learn well. We can use a larger k. On the other hand, there are also computational issues, finding the k nearest neighbors. So the trade-off is also computational. But what about, can we use the data to automatically choose k? So let's have what's called a cross-validation approach. Okay, so cross-validation. And there are different ways to call this. There are different terms, but the idea is simple. You partition your data into training and test data, and some people call this holdback data. And then you train on your, so step 1, partition. Step 2, train on training data. And step 3, test what you trained on the data that was held back. So recall, what you partitioned into training and test, or perhaps training and validation data, you're going to see how well you perform on the data that you held back. So you validate your approach. And you can do this on different values of k. But now, suppose that the specific partition that you chose between training and test data, suppose that in the complicated region that we were seeing earlier, the shaded region, suppose that by chance, in your training data, it's mostly blue, and in your test data, it's mostly red. That's certainly possible, right? So here's another possibility. Run the cross-validation multiple times. Multiple times, choose different partitions. For each of these partitions, for different values of k, train and test. So now let me kind of write a possible pseudocode for what to do. So loop over different partitions into training and validation. And by looping over different partitions, this will not necessarily ensure, but it'll reduce the randomness in your approach. Step number 2 in our pseudocode is going to be loop over different values of k. Inside our loop, we train on the training data. And by train, what we really mean, we derive a k nearest neighbors, NN, classifier from the training data, validate it, validate the performance. And now I've collected data for different k on different partitions, and I aggregate the performance. So in other words, I don't look at the performance for different values of k only on one partition. I look at the aggregate performance over all the partitions and select the k, then in aggregate offers a good trade-off. Now recall, we can quantify the trade-off. We can say stability costs us 13 units per unit of stability, and accuracy costs us 7 units. We can do that. So we can recall the optimization material. We can have a multi-objective cost function, and that multi-objective cost function can have possibly a linear term in the two different main criteria that we want to optimize for. And then this overall cost or utility function, we're selecting the k that's best for that. And again, it's not a k over a single partition, it's a k over multiple partitions. All right, so let's move on. We know how to choose k in the k nearest neighbors approach somewhat automatically, but let's now look at a completely different approach for classification. And we're going to look into this approach in greater detail over the next several modules, and it's a linear model. So suppose that we're looking at two-dimensional data, and the xj is coordinate along dimension j, and that's why I'm summing over the dimensions, and xj is going to be multiplied by an estimated coefficient beta hat j. And to that I add an offset term, beta hat 0. So this is going to be, as a function of locations of x's, this is going to be my y hat. And now I perform a decision on y hat. If y hat is greater than threshold, red, else blue, okay? Or blue else red, it doesn't matter. So basically, I am trying to form a linear function. I'm learning the beta coefficients from the training data, and then it's going to be a threshold decision. Now, why is a linear model commonly used? We've talked about these things before. In many problems, they're reasonable. So for us, for this classification problem, it often works well. That's what being reasonable would really mean. It's simple, so it's algorithmically tractable, mathematically tractable. So as we're going to soon discuss, there are ways how to learn these beta hat coefficients. And as I've said multiple times, many systems, just like many systems are well approximated as convex, many systems are well approximated as linear. And because of that, a lot of computational and analysis and algorithmic machinery has been developed for this stuff. So we have a mature understanding. And indeed, in a few modules, we'll look at a quadratic approach. We'll go beyond linear. Okay, so linear classification. How do we calculate the coefficients? So we want y hat to be x transpose times b. And recall that x transpose, these are the locations of the training data. It's given to us. We want beta hats that make y hat look good. So we're interpreting it as a linear function. F of x, function of x, is x transpose times b hat. And Gauss, in the latter part of the 18th century, he came up with the least squares method. you minimize the sum of the squared errors. So beta is going to be a vector, okay? Beta hat 0, beta hat 1, beta hat 2. In our case, the number of dimensions is 2, and because of that, you have a DC offset, beta hat 0, and for the 2 dimensions, beta hat 1 and 2. And for the 2 dimensions, we're going to have a length 3 beta vector. And for each length 3 vector, we're going to be summing over the capital N elements in my data set, and we'll be taking the square of yn minus xtn beta. The lowercase n is sample number n, and recall that x is a vector, xn is a vector, and we're taking its transpose. It's a column vector. In our case, it's of length 2, and xn transpose is a row vector, and beta is a column vector. Row times column is a scalar, okay? So for a given beta, we're calculating this sum of squared errors as a function of beta, and it can be expressed as y minus x beta transform. X is now a matrix. We stacked together all the xn's, and y minus x beta transform is multiplied by y minus x beta. X is a matrix of size n by p, n rows, p columns. Y is an n vector of training classes. Now, this is an interesting point. In the binary problem, y could be 1 or negative 1, 1 or 0, whatever numbers you want to assign. If you have ternary classification, it could be 0, 1, 2. Now, what if you really care about errors between the blue and the red? You don't really care about the green that much. So the blue and the red, you can space them far apart, like 0 and 10. And the other one that you don't really care about could be in the middle, could be a bit above, could be a bit below, but you can construct your numerical labels in a way that help you achieve your design goal. So overall, we've expressed the error as a function of the vector beta. We want to minimize the error as a function of beta. We take a derivative with respect to beta, and this is going to be not really a regular derivative, but because beta has multiple coefficients. In our example 3, this is a sort of a gradient. And we want x transpose times y minus x beta to be equal to 0. So recall that in my earlier expression, error as a function of beta was y minus x beta transpose times y minus x beta. In order to ensure the optimal beta, this is equal to 0, a 0 gradient. And this tells us that x transpose y is equal to x transpose x beta. And the closed form solution of the least squares method, which is often called pseudo-inverse, beta hat is x transpose x inverse multiplied by x transpose y. So we took the x transpose x, we multiplied both sides of the equation by x transpose x inverse, and that gives us that the optimal beta hat, is x transpose x inverse multiplied by the other side, x transpose y. So closed form, given a training vector beta, and given the data x, a closed form solution for the optimal betas. Or rather, I should have said the training vector is y, not beta. The known labels are y. The data is x, and we've calculated beta in closed form. So results for linear classifiers. Now recall, it's a linear function, and because it's a linear function, there's going to be a straight line, and that straight line is going to separate between the two regions. And below, we're red, above we're blue, and again, it's a line. We're only going to have two regions, and the separation between them is a straight line. So it's very stable, but terrible bias, lots of error. Whereas earlier, when we chose in a reasonable way, when we chose k and the k nearest neighbors in a reasonable way, we got better performance. So to wrap up our comparison between these two classifiers, the linear model is very stable, but biased. The nearest neighbor is depends on the k. It can be somewhat less stable and somewhat less biased. And what we saw is that you need a moderate value of k, and at least in principle, you can try to evaluate numerically what's a good k. Now, when I said automating the choice of k, you don't need to think about this in terms of, will the optimal k be 9 or 11? Rather, you can think about it, do we want the optimal k to be 50, 30, 20, and of course it should be odd numbers, so approximately 50, approximately 30, approximately 20, 15, 11, 9, so ranges of k's. And yes, we will be able to differentiate between ranges of k's, and we'll be able to identify automatically what's moderate for that problem. Now, you could interpret the nearest neighbors approach as better in quotation marks, but it suffers from the curse of dimensionality because in higher dimensional problems, neighborliness is difficult to analyze. And in particular, there's going to be a scarcity of neighbors in high dimensions. And because of that, for the high dimensional problems, oftentimes people are going to use a linear model or a quadratic model. And that's because the curse of dimensionality and the problems in defining neighborliness really mean that it's very noisy, the k nearest neighbors approach. So that'll be all for module number 26, and we'll continue next time.